welcome to Coding Adventures. In today's episode, we're gonna implement flat fill. We're gonna implement flat fill on the canvas, and hopefully, towards the end of the stream, we'll be able also to animate the flat fill and see how this is working. So you probably are familiar with the flat fill algorithm from the various coding challenges problems that you can find out around. And in most implementations, flat fill is implemented in a non-visual way. So I thought that it's better to implement flat fill in a very simple way, but visual. All right, so let's get started. All right, so I'm here in my coding editor. And before we start to implement the actual flat fill algorithm, I'm gonna create a little bit of a plumbing just to, to be able to better visualize flat fill. So let me go here and define a function, the function loop. This is the basis of animations in p5.js library in codeguppy.com. And this function is basically called automatically by us by the browser about 60 times per second, so we can create nice animations using this one. So what I want to do inside the loop here, I want to use the mouse and draw some shapes on the screen. Of course, as long as I'm keeping the left mouse button pressed. If I'm not pressing, I can move the mouse freely. So I'll say if mouse is pressed, I think this is the right constant. I'm gonna do a line from the previous mouse position to the current mouse position. And the good thing is that we have some predefined variables here in the p5.js platform that gives us this coordinate. So it's from p mouse x and p mouse y to mouse x and mouse y. Actually, these are floating point numbers if I'm not mistaken. So it doesn't hurt just to make them integers. So let me use the floor functions, or math.floor is kind of the same. And let me see if I get anything. Hi. Probably this is the simplest and easiest drawing program ever created. So anyway, that's not the purpose of today's lesson. So we said we want to implement flat fill. But I put this plumbing here, or this coding here, just to allow us to develop some sort of closed shapes. And then when we go inside, either we press right mouse click or we press a certain key, and then we automatically fill this area inside the shape. All right. And as you can see, this is not a geometric shape like a circle. So it's a totally free-form shape, and the algorithm will have to figure out how to go and fill this area. Probably you remember this one if you played with paint back in the days. This was a very fun activity a couple of years ago. All right, so let's before we actually go and implement the algorithm, let's see what else Wikipedia says about it, and then we'll also go on the notebook and start to plan a little bit around. So we're looking here on Wikipedia, and we can see the flat fill in action is this picture here. As we can see, this area starts to get filled. We even get an implementation here, or an algorithm. It says flat fill, if node is inside, if it's not inside, return. Makes sense, right? We need to be inside the shape. Set the node, and then perform flat fill one step to the south, to the north, west, and east. So basically, this is kind of a recursive function, and recursivity is something that we never tried here before on the channel, but it's a very simple concept. So, all right, we're gonna try to implement this kind of algorithm first. And I just want to let you know that for flat fill, there are countless of algorithms available. This is one of the most studied problem. Also, you can see here in these pictures various flat fills, how the area is filled here in a certain way, and on the left in a different way. All right, so enough with theory. Let's get a little bit our notebook and discuss what we saw there about the first algorithm. So let's suppose we have a canvas, right? In our case, this is 800 by 600. But you know what, actually I'm gonna make some verticals and horizontal lines, basically create some really big chunky pixels here. And this is because flat fill, when we work with flat fill, we are actually setting pixels on the canvas, so we'll need a way to access these pixels. But anyway, bear with me, just a few more lines. These are very chunky pixels, as you can see. So let's say we have a shape here drawn somewhere. And what it means to have a shape like we draw with the mouse, it means to have certain pixels set or colored, just like that. So if we have a small circle, perhaps this kind of pixels, or this is more like an ellipse, this kind of pixels are all set. So now if we want and go with the mouse inside here, we go with the arrow of the mouse and we initiate a flat fill here. That algorithm said, well, first we have to set up or to set this particular pixel, and then look at other pixel, one to the right, one to the left, one up, and one bottom, and invoke again the same kind of function that did this, that set this pixel basically. So our function will be in charge just setting up this particular pixel, then discover what are the coordinates of the adjacent pixels and invoke again the same functions. And in this way, this pixel will be colored, this one, let me color them with a different color, perhaps with this color. And then once we are inside the function again and it's coloring these pixels, of course, we'll do the same and we'll discover the pixel on the bottom. And here it's an interesting situation because we reach the edge, we don't consider those pixels as discoverable, so we don't go in that direction. But here the function can go to the left, and here can go up, and here can go also to the left. So in this way we fill up the entire area, of course with only one single color, but here I represented multiple colors. Alright, so basically if we are looking back to Wikipedia, I think that's what Wikipedia said. Let's double check again. So Wikipedia, flat fill. Alright, this was the flat fill page. And yeah, we're gonna say set the node, and then see, this is our flat fill function that I was mentioning, and then basically re-invoke the function again for the adjacent nodes, the one to the north, to the south, east, and west. And because we are invoking the same function, this function is getting to be called a recursive function. All right, so I think we are on something here, but we need something more before we actually start to attack the problem. We're gonna need in our toolbox a few functions. We need a function to set a pixel on the canvas at certain x and y coordinates, of course. We need a function like we encounter in this case to check if a pixel is set. So maybe call isPixel at certain x and y coordinates. We need to, when we are on this square, for instance, we need to check for this pixel. And perhaps, I don't know, maybe we should have also a function, I think comes handy. If an x and y coordinates are valid, for instance, what if somebody tries to initiate the fill in here? Let's say all these pixels are filled, but of course we don't want to go forever to the right or to the bottom here. As long as the xy will not be valid, basically goes outside of the canvas, we consider that we are done with the filling. So let's go therefore and implement these three functions here in the code, and they're pretty easy because we already have support in the in the codeguppy environment that we are using. But nevertheless, I think that support is kind of spread a little bit. So let's focus this into three functions. So let's define the three functions that we said. So the first one, function set pixel, and at a certain x and y coordinate. And for this one, we're gonna use plain and simple the point from the p5.js library. We can say point xy. Eventually, we can we can create the point in a certain color if we want. 255 maybe 0, 0, and yeah, that's it. So that means red, right? So RGB. So when we're gonna set the pixels, should be in red. Let's make sure that this we're gonna put this between a push and a pop so that attributes don't spill outside. All right, because here we are drawing with black, and then when we are filling with red. So it should give us a little bit of a contrast. So we have the set pixel function. Let's define now that is pixel or get pixel. I don't know. Naming it's not that important, but we should come up with a name that is easy to remember and use. So let's say if it's a pixel set at this coordinate, right? Is pixel X and Y. And for this one, we're gonna use, we have available in p5.js. Let me consult the documentation really quick, the get function. And the get, where is the get? All right, this is on an image. All right, we're gonna use this form. So you specify the coordinates and it comes back and returns an array RGBA. So basically it returns the red, green, and blue plus the alpha of that pixel. So we're gonna use that that construct. So let's take the argument, the return value in an AR variable. So we're gonna say get X and Y. So how can we determine based on RGB if it's a pixel at that coordinate? Let's say alpha is greater than 0. So means, because here we are using RGB and alpha model. And if you're not familiar with the RGBA model, leave a comment and we're gonna create a separate lesson about that one. So let's say return true if AR of 3 is greater than 0, right? So this one returns RGBA. So like an array like this. And then if alpha is greater than 0, normally should be 255 for really opaque colors. 0 is totally transparent. But let's say a pixel, it's a pixel at a certain position if it's not totally transparent. If it's a little bit of opacity there or it's totally opaque, and it's fine, we consider a set pixel. In some algorithms, they take a color, for instance, if they encounter black on the edge, or if they encounter a different color than the color that started the fill inside. We can implement that way as well. For now, let's say that we want to fill all the transparent pixels inside the shape. So initially, when we run the program, all these pixels on the canvas are transparent. We are drawing with the mouse a shape. These pixels are not transparent anymore. They have alpha 255. They're totally opaque. They're drawn also in black. And when we're gonna click inside here, we want to fill all the transparent pixel until they encounter one pixel that is basically not transparent. So that's the purpose of this function. And then we said that it's good to have another function here. Let's call that one, I think we name it valid. If a coordinate X and Y is valid, basically if it's inside the canvas. So I could have named it inside canvas. Kind of the same, right? So the return is pretty simple. If X is greater or equal than 0 and X is less or equal than width minus 1. So on horizontal from 0 to 799 and Y, the same for Y basically, and Y greater or equal than 0 and Y less or equal than height minus 1. All right, only in this case a pixel is valid or it's inside the canvas, otherwise it's not inside the canvas. Let me save this one, flood fill, and share it with you on the chat. For now it's not doing too much things, but feel free to load it from time to time as I'm progressing here. Flood fill. All right, the program is on the chat. And now it's time to implement that flood fill function, right? So we'll have a flood fill function. Let's name it fill, flood fill. There's another fill function in the p5 library. We are kind of overwriting this one, but it's okay. Fill, and we'll specify where we want to start the fill, right? So we go at a certain coordinates and they say fill. And from this point on, we should basically fill those transparent pixels. How do we invoke this function? Well, either here in the loop, we can check for the left mouse. If left mouse button is pressed, basically fill inside, or if I'm pressing a key, I'm gonna select to press a key for now. Function key pressed. I think it's okay also to check for right mouse button, but I'm thinking that we have to do a little bit of duplication because loop is happening so many times. When we're pressing the right mouse button, we may trigger the function multiple times. So we have to do duplication. Anyway, that's the reason I'm thinking it's better to have a key pressed here. And we can check if I'm pressing a certain key or any key here, basically. So let's invoke it. We are calling fill at mouse X and mouse Y, right? Or let's do the same like we did above, just to make sure that we have integer values. And we are here inside, and what we can do, we're gonna, for the moment, we're gonna just say print X plus Y, like this, or say fill at, and let's make sure that these things are invoked, these functions are invoked correctly. I'll run. Anyway, it doesn't matter, I can draw, I press a key, yeah. And each time I'm pressing a key, basically I can initiate a fill at a different coordinate as I'm moving the mouse. If I'm not moving the mouse, of course, the same coordinate. If I'm moving, yeah. So we have the plumbing in place. At this moment, we have everything that we need, we just have to focus on the fill algorithm. So let's remember, we are taking back the notebook, right? And we said we're gonna implement first that simple algorithm that also Wikipedia described, that we're gonna try to set a pixel here, and if basically, of course, first of all, we're gonna check if this pixel is set, right? So if we are if we have already a pixel and we are going with the mouse inside that pixel and we try to fill it, it's best to check it. Also, when the recursion will go on, also that check will be pretty important. So anyway, we're gonna check if this pixel is set. If it's set already, we don't do anything. If not, we'll set it, and then we're gonna invoke the function again in the 4 corners. And there are other variants that go in 8 directions. This we are going in just in 4 directions for now. So let's see if we are able to implement the algorithm correctly here. Let's check first. Let's do these checks. If the pixel is set, we can also check if it is outside the canvas. So if it's not valid, if the coordinates are not valid, what can we do? Of course, we can return. So for instance, we are trying to fill outside the canvas, we are returning, or maybe the flat fill will go outside the canvas. Now, let's check if is pixel, if it's already a pixel at these coordinates, a pixel set at these coordinates, also we are returning, right? We are not doing anything in this case. Otherwise, let's set the pixel. So we're gonna call set pixel here, set pixel at these coordinates, and let's just run the function for now, see what's going on. So I'm pressing X at different coordinates. Notice that I get a small red dot there, which is normal. Now what I want to do is actually draw a shape first, and then when I'm pressing X, of course, get this point, but then go and on this direction, and then go on this direction, on this direction, and on this direction. Let's see if we can achieve that one. So a recursive function is a function that invokes itself. This is not a lesson about recursive functions, but if you are interested, we can talk about recursive functions in the future. For now, let's just say that exactly like we can call any function from a function, we can also call this function from within this function here. So let's call it. Now we want to do the same logic here basically, and why we are calling it? Because the logic that we apply to this pixel, we want now to extend to the left, right, top and bottom and apply the same logic. So what better way than to call again the same function, because the function has already the logic, right? So we'll call again the same function for x plus 1. So basically we are moving to the right, and the same y. And then we are calling the same function for x minus 1 and y. We are moving to the left. And the same function, we'll keep this time x constant. So we, let's say y minus 1. So we are moving to the top. We are decreasing y. And then let's move to the bottom, x and y plus 1. All right. One hint here. Save the program before you run it. Recursive functions, if we create a mistake here, we'll just freeze the program. All right. So function looks correct, looks like the algorithm that we propose to implement. Let's run it. And we first draw a shape and go inside, press a key. Boom! Let's try it one more time. Boom! It's just working perfectly. All right. Let's just divide this shape into various shapes, and perhaps even more. So let's try to run it now. Here, boom, it's working, right? Let's divide it. It's working fine. It's working fine. Let's have a bigger shape this time. Perhaps one like this one. Let's not make it go outside. We'll cut that exit line and then press X. And now we have a problem. It says here, maximum call size exceeded. So let's run it again and I'm explaining what's happening. If we run it for a small shape, it's fine. If I'll try to run it for a bigger shape, this time will fail. And the reason is in the recursion here. Each time we are calling the function, of course the computer or the JavaScript engine will have to remember where to come back. So after this function finishes, we'll have to remember to come back after the next line and so on. And not to mention that this function call are function inside function. So we are calling first time the field, and the field will call again field, and that field will call another field and another field and another field. So imagine that this simple call that we initiate from the outside will get exploded in thousands of calls. And the problem is that all these calls, in order for the computer to remember where to come back and for other reasons, it allocates a small chunk of memory. And this small memory chunks or memory frames or stack frames, how they are called, are allocated on a structure called stack. And the engine allocates about 1 megabyte of memory for stack, which seems a lot, but it's actually not that much, because in the moment we'll have thousands of calls, and if for each call probably we need about maybe 80 bytes of memory, we can calculate. We'll see that we can only do perhaps only a couple thousands of calls, but for a bigger shape like this, when we're gonna initiate fill, here inside there are many pixels, probably more than a couple of thousands, or even if there are not that many pixels, actually because of the those frames, they are not 1 byte, will go beyond the allocated kind of 1 megabyte for the stack. So, well, as you can see, this one or this algorithm is working fine, but only for small shapes. And this is very important to remember. This is a pretty popular algorithm, and you know, you may find it implemented only in this kind of implementation with a stack, and as you can see here, it has a problem. Otherwise, it's working fine. I created here a pretty intricate shape, and this was no problem for the algorithm. But still, we cannot work with bigger shapes. So, what's the solution? Well, one solution to the problem, instead of using this predefined stack that the engine is putting at our disposal to use, we create our own stack. And in the moment we create our own stack, we can basically use as much memory as we want. So if we have a 64 gigabyte of memory kind of computer, we can use up to that much memory, which is a lot more than the 1 megabyte kind of that computer allocates for the so-called stack structure in the engine here. So let's see how can we re-implement this function, but not rely on the built-in stack and not have basically a recursive function. So let's leave this one alone. Eventually we can call it fill recursive, but if we call it fill recursive here, we just have to call it here as well. Otherwise, this fill won't find what function to call. So I'm trying to run it. Oops, it's not working. Oops, because here fill recursive. Let me see if I didn't mess up that program. Yep, it's working fine. So let's create another function. This time we're gonna call it fill again. Takes x and y. And we want kind of the same logic here. We want to go in the 4 directions, but what is different? We don't want to make use of recursion. We don't want to make use of the stack from the language, but we want to create our own stack. And what better way to create our own stack than to have an array? And array is the perfect structure in JavaScript, since it has already those stack-oriented operations, like we can push into it and pop an element from it and things like that. So let's have an array. Let's call it this one fill stack. Fill stack sounds pretty right. And we initiate it with empty, right? And the way we want to do, we want to push basically these coordinates on the stack and then kind of go forever on the stack and try to pop up elements from the stack until the stack is empty. So let's start with pushing the first set of coordinates on the stack. As I said, and then we're gonna try to pop it out from the stack. But the thing is here is that in the moment we pop it out, of course we put other elements on the stack. These guys, basically the left, right, up, down coordinates there. And the stack, even if we pop out elements, other elements will get added. So the stack will grow for a while until it's basically emptied at all. So let's put the first element. So fill stack. This is an array, right? So we can use the push method. And we need to push 2 values. We can push them in a structure, in a small object, or like in a small array, like this, push x and y. And now we try to go on the stack as long as fill stack.length is greater than 0. So as long as we have elements in the array, basically in this one, we'll call this array a stack. As long as we have elements on the stack, we want to extract them and basically try to work with the elements. And of course, initially we have at least one element, which is this one, right? So let's extract it. Sounds counterintuitive to put it and extract it, but the logic is still handy because as we extract it, we'll push other elements. So this one will be an array, right? So we are extracting in an array, which is fill stack.pop. We are using the pop to extract the last element. We are putting the last one and we're extracting the last one, which is fine. And then what we want to do is we want to implement this logic here, the same logic like in the fill recursive. Let me show you a trick here, because this one it's an array and because it contains 2 elements, we can use the destructoring syntax like and obtain the xy directly, so we don't have to extract them from the array after that. And now I'm gonna copy this code just to show you that it's perfectly exactly and identical with the one from the recursive version. So let's review it. We are extracting, we check if it's valid. If it's not valid, actually it's not identical. If it's not valid, we are not returning from the function. We move on to the next element on the stack. So instead of return here, we can say continue. And the same, if it's a pixel there, we continue. But of course, if there's no pixel and the coordinates are valid, this line will be encountered and we basically, boom, set that element. And after we set, what we have to do, exactly like here, go and check the neighbors, the left, right, up and down. And this time we won't invoke this function, because if we are invoking again, we go back to recursivity. But instead, we are going to the stack, and we are pushing on the stack those coordinates, basically x and y plus 1, and then we are pushing x and y minus 1. Let's push them in the same order. Yeah, let me just take them from here, just to think how to push them. But instead of calling it, we said that we call fill stack dot push, and we have to push them as an array. Just like this. All right. So let's inspect the function really carefully. And as we can see, inside the while, we are pushing some elements. At the beginning of the while, we are extracting elements. Initially, we are pushing more than we're extracting, but after a while, we'll push less and less because all these kind of areas get filled up, so we are pushing less. So it's kind of the same algorithm like before, but this time we implemented our own stack, and hopefully, if we don't have any mistake here, this version will allow us to fill bigger shapes. So let's try it. I'm gonna run it, and let's call fill, not fill recursive, when we are pressing a key, and we'll run it. Let's try one small shape. Okay, algorithm is running at least, and let's try a big shape and press X, and come on, nothing. It worked! Yay! What we noticed though, that it's a little bit slow, and when we fill that big shape, that was pretty obvious. Let me run it again for a big shape. And this is not the problem of the algorithm, but I suspect that there is the problem of that set pixel that we created, that helper function set pixel, even get pixel. You know, in JavaScript, when working with HTML5 canvas, when we try to access individual dots like we are doing here, it's not very recommended. It's much better just to get all the dots in the image, and then basically set the dots that we are interested in, and then update the dots eventually. So we can do that. In p5.js, there is a construct for that. It's pixels, if I'm not mistaken. Yeah, pixels, load pixels, and then we can access the pixels array and then call update pixels at the end. So we can use that one, but I think I discovered at one point a small bug with that that construct from p5.js. I'm not sure if the bug is from in p5.js in general, or if it's just in the version of p5.js used by this environment, or maybe they fixed it in your version. I didn't check, but nevertheless, I want to avoid that function, and I want to use instead, since we are here basically in an HTML5 environment, I want to access directly the canvas data using a built-in function that we have in HTML5, and that's get image data. So let's search for that one, HTML5 get image data. So this function is not in a library, it's actually a bare metal support function in all the modern browsers. Yes, this is the function that I want to use. And the way we're gonna use it is basically we have we need a context for the canvas, and call get image data. In our case, we'll just call it with 0, 0, and 800 and 600. We want to get the entire canvas in the image data function. And image data has inside, actually, this is a structure, but has inside a data property. I think we can find it here. I know for sure there's a data inside, but let me see if I can find it here. This is a very good documentation from Mozilla Development Networks. So get image data, put image data structure. Let's see it. properties. Yes, so that one is returning the structure that has inside the data, which is actually the array of pixels, and then the height and width. We are not interested in the height and width because we know already that it's 800 by 600. So that's one thing that we need. We need this function get image data, but this function get image data is actually using the context. In p5.js actually there is a predefined variable called drawing context. So we're gonna use that one, p5.js drawing context. Let's see this one. Yeah, drawing context. All right. So let's play a little bit with the function in a separate code, just to make sure that we get the function right, and if it's working right, we move it in the other program. Again, what we plan to accomplish here is that the set pixel function is a little bit slow, so we want to optimize that a little bit. It's not necessary for the flat fill. As you can see, flat fill works here, but nevertheless it's something that we want to do. So let's say we set to obtain the image data, and is the drawing context. This is the p5.js predefined variable. Yeah, drawing context. All right. Dot, and now we're gonna invoke get image data, and we're gonna invoke it for 0, 0, 800, 600. So we obtain the entire canvas kind of in this image data structure that should have three properties: width, height, and data. So let's access the data here. It's image data dot data, and now if everything went correctly, we should see the size of this array, which is, all right, let's run it. Oops, something is not right. Oh, I kind of printed let's put data.length, and if I run it, yep, sounds correct to me. So why is that value? Is because they're 800 pixels by 600 pixels. Oops, 800 pixels by 600 pixels, and each pixel has actually 4 bytes allocated, one for red, green, blue, and one for alpha. So times 4, yep, 1,920,000 bytes. So about 2 megabytes of data is allocated for the canvas. All right, looks fine. With this information, basically, yeah, let's try to put it here in the program. See if we can optimize it a little bit. Let's have this variable like a global variable here. And now what we have to do, just before the fill actually, or inside the fill, yeah, inside the fill, yeah, inside the fill we have to, we don't have to set it like a global one. Yeah, inside the fill, before we are actually working with anything inside, actually it's good to have it like a global. Yeah, let's have it like a global function, global variable. And there is a reason for this one. It's because we want to access the pixels from different functions without passing them around via arguments. So here before the fill, or actually even here, we can set that image data. We can extract all the pixels using the get image data. We invoke the fill. We now have to modify the fill to kind of work on this array of data, and then at the end, this is not enough, we have to invoke put image data or something like that. Let me see which one, it's the other one. Yes, put image data. So after we do all the modifications on this array of numbers, we have to invoke put image data. So drawing context dot put image data, and of course we're gonna put what was the syntax here? Yes, the image data and what coordinates we want to put it back. So we're gonna put the image data at 0 and 0. All right, so this maybe sounds a little bit scary. We are going above and beyond p5.js. This is HTML5 Canvas API, but it's not that bad, right? So we are getting the structure, we try to invoke fill, and now we're putting back the structure. Now fill, we don't change it, but what we're gonna change the set pixel and eventually isPixel. These two functions that work, instead of using the point here, we want to basically work on this structure, right? So the set pixel, we don't want to use the stroke, and we don't, let's make it simple for now. Yeah, let's make it simple. Actually, let's create two versions of these functions. So these are set pixel with an underscore at the end. Underscore, it's a valid sign to use it in symbols, in variables. It's not preferred, but anyway, I just put it there just to render those functions unusable for the moment. We could have just commented them. So let's see how these functions will look like when working with this structure, right? So first of all, let's access that pixels inside, or that data. So the pixels is image data. I think we have it global. Yep. So it's image data dot data, right? Yep. And now, if this is a linear structure, it's not like a canvas, it's not a 2D structure. So we need to find the index of the pixel in this coordinate, but it's pretty easy because it goes from the top, and each line is from the top to, and goes like that to the bottom. So the index of the pixel, basically I, should be, okay, so it's y. Y, it's how many are on vertical. So basically how many lines times width. Width is 800, right? And then we are adding whatever x is remaining here. So that should be the index, but just multiply by 4 because there are 4 bytes for each pixel, right? So coming back here just to understand what we try to achieve here with this fancy set pixel. If it's not working, we always come back to the other one. So let's say we want to set the pixel, this one, right? That has coordinates 0, 1, 2 and 0, 1, 2, 2 and 2. So first of all, we multiply y, which is this one, with how many they are on horizontal, and then we are adding whatever fragment is left here, x being the fragment, right? So sounds kind of okay, if I'm not mistaken. So the index should be kind of okay there. And now with the index, we can go inside the structure. Yes, we can go inside the structure and say pixel of I. So the first one should be red, right? And we'll just set it to 255, like in here we did with the stroke. Pixels of I plus 1 should be the blue. We are setting to 0. Pixels of I plus 2, RG. No, this should be green and this is blue. Is also 0, but we set the fourth one, the alpha, to 255, right? Because we want to have really opaque pixels. So that's kind of sounds okay to me. This is the new set pixel, that it's setting a pixel inside this array, and we basically have to do the same for the get pixel here. So the first two lines are the same, right? We access the pixels or the data inside this structure, and the index of the pixel should be the same. And now we can implement the same logic like here. If alpha is greater than 0, then we are in good shape. It means that that pixel is set. So we are returning if pixel, this is alpha in our case, if pixels of I plus 3 is greater than 0. All right, sounds okay to me. So let's see the logic again. Before calling fill, we are getting all the pixels from the canvas in this structure. We are invoking fill. Fill just does its job. Inside fill, we invoke set pixel is pixel, and when these functions will be invoked, they'll work on this structure of pixels, which should be very, very fast because they are in all in memory. Should be really, really fast. And then at the end of the computation, we are sending back the structure to the canvas to draw it basically there, because otherwise if we are just setting the pixels in that pixels array, these pixels will remain set in memory. So let's run it. I'm gonna save it, run it. Small shape. All right, still runs. Big shape. Okay. Not super fast, but it's much faster than before. Much faster than before, actually. And let's create a pretty complex shape here that goes around the other one, goes around, and let's fill it. All right, looks pretty much okay. So I think we implemented the algorithm correctly here, and we also optimized these functions to work with image data instead of having those simplified pixels. So let me close this once. All right, now I want to show you something something really interesting before we move on, without going into the technical details. So we have this algorithm, and we said we are removing here the elements with pop, but you know, the pop removes the element at the end of the array, basically. So that's why this looks like a stack. But you can also remove the elements at the beginning of the array, and that will have a pretty interesting effect. But of course, in order to kind of see this one, we'll have to let's first try to animate them. And hello there on the chat. I'm glad that you like the videos. Let's try to animate this one. All right. So perhaps we can return back to the simpler function, or we can keep this one, the set pixel or the other set pixels. Yeah, let's comment these ones just not to be in the way. We can keep these ones, the big ones. Yeah, I think we can keep the more optimum functions, or we can also return to the simpler functions. But anyway, the purpose is now to animate the fill, to see exactly what's going on, how the fill is happening, because here when we are running it, it happens so fast. So we have a very complex shape, we are running it, and boom, it's done. But does the fill, the paint, goes into left and right, up and down like we design it here? Let's try to animate it. So the way we're gonna animate it, I'm thinking, all right, let me think a little bit. I'm thinking to go inside basically still to do the flat fill at once. That will be the easiest way, rather than go back here and break the algorithm and make it fill 1 pixel per frame or something like that. I think it's much easier if I'll still do the fill in one shot, like here, but each time I'm setting a pixel, actually I want to store it in an array, in a structure, and then frame by frame go and draw pixels from this structure, right? So that should give us kind of an animation effect, I hope. So let's have a structure here, some sort of pixel structures. Let pixel structure, pixels. Yeah, but it's not the pixels from the inside here. So fill pixels. Let's name it fill pixels. That is an empty array, right? We started with an empty array, and now we go inside the set pixel. We let it be like it's doing its logic here. We don't change it, but once it finishes its job here, we want also to put that kind of pixel, this X and Y, into that structure. So fill pixels dot push. We're gonna push the X and Y, right? So store the pixel that is set, the set pixel in an array that will be used later on for animation. So we just store it there, right? And eventually set pixel will happen many times, and we should be able to store perhaps here 1 million pixels. 800 by 600. Actually, there are not 1 million pixels on the canvas. But we're gonna store here tens of thousands of pixels. So that's fine. And then inside the loop, since we have an animation loop here, we want to basically animate the fill, or right? So animate we'll call animate pixels. Yeah, animate pixels. Let's have a function here, animate pixels. And what these functions will do, now we're gonna try to animate all the pixels that are here, right? So we also need, yeah, we need an index in the variable to see a kind of a pointer inside this array. So pixel index, pi. So this one will start at 0, then we'll increment it to 1, to 2, to 3, and so on. So as long as pi is less than fill pixels.length, right? .length -1. I think we are good in .length. Now, what we want to do, let's use a simple. We can manipulate the image data again, but I don't want to do calculations right now. Let's use a simple point here, right? So we're gonna use a stroke, and perhaps fill it with red, RGB. It's a problem because we filled initially with red. Let's fill with opaque red here, and initially when the function does its job, or when set pixel does its job, let's fill it with a lighter red, kind of a less opaque red, right? So maybe here with a 20. This is for the opacity. So this is R, this is G, blue, and this is alpha. And it should be still fine, because when we are checking for if a pixel is set, or we are checking if it's basically a little bit of, if it's not transparent, if it's greater than 0. So 20 should be still fine. We should not change the algorithm. Yeah, that should give us basically this ability. Initially, when we fill with a little bit of a lighter red, and then when we animate them, we actually go and use red with opacity 255. And hello to Colombia as well. So we are using a stroke, we said, and now we have to put a pixel. So we can put a, we have to extract the pixel here and use a point instruction. So let's extract it. We're gonna use the destructuring here, exactly like we used before. And we have it in fill pixels, right? In fill pixels of pi. And then we increment pi. Oh, fill pixels is an array, not a function. And then we increment pi, right? So we extract that one. We plot it. And then we increment pi like this. Okay, let's put it here just to be fancy. All right. So we just added these animate pixels. That should run for this fill pixels. Initially, that array should be emptied. It's empty. We add pixels to it once we fill. So let's run it and see if it's if we get something. I'll create a little bit of a bigger shape and press a key inside. All right. It's working fine, although it's working up and down. And let me fix this one, because I already said it's working left to right and then up to down. And the reason is I'm thinking, yeah. See, what we did, we converted the recursive version into our non-recursive version that uses a stack. But in the we kept the same kind of coordinates, like here, x plus 1, y, x minus 1, y. Thing is here, this one will get called first, right? After set pixel is called this one, so it goes to the right and then goes to the left. Here, when we are popping in the inverse order, so it goes first down and then goes up. So let's inverse them, because removing from the stack goes in different direction. So this one should be first. It doesn't matter, really. It's just because I want to keep consistency with the recursive version. All right, so this one should be totally the other way, y plus 1, y minus 1, because pop here, we're gonna read them in the other order, so x plus 1, x minus 1. All right, so should be fine. So if we run it, and let's run it for a small shape, but a complex one, x, all right, left to right, it skipped there some lines, Let's see if it, and I'm pretty sure it will gonna fill those up, because notice the light red in the back is totally, okay, it's now handling that one. Coming back. Isn't this cool? So we can see how this fill, it's doing its job. Well, there, because of the pixels, it went on a little bit on a vertical, but we're done. Let's try it again. Let's try to do two at the same time. Now we cannot do two at the same time. And you know why? Good that it didn't crash, because we didn't code it for this one. If we'll do two at the same time, basically we'll have to keep multiple fill pixel structures in the memory. Not only one, because right, we have to keep one fill pixel structure for each the shape that we are filling. So I think we can handle this one. Actually, it should not be pretty difficult. Let me try. If I'll mess it up, I'll revert and keep this simple version. But let me say we'll have a fields array. This array keeps all the fields structures that we want to animate. So not only one, it will keep a lot of field structures here. And just checking the chat here. No, we are not. I'm not using the recursive function. Just for the people that arrived late to the chat, we started with the recursive function, and that recursive function proved to be problematic for big structures. If we try to fill a big areas, we are getting Stack Overflow or maximum stack exceeded. So we converted that recursive function in an iterative function using our own stack. So that's what we are doing here. So let's get back to the animation. We'll have one of these fill structures. And now what we want to do, before we actually initiating a new fill, let's, in this structure that is an array, let's go here and create an empty object, or some sort of an object that will keep the, that will have some pixels array, right? So we'll have a pixels that is an empty, and that pi coordinate, all right, or pi index. So I'm thinking again, all right, so we'll have for each of the fill structure that I'm trying to fill, one of these small structures with the pixels and the pi and an index inside. So that should be kind of okay for now. And now when we are animating the pixels, we have to loop through all these fill structures. So for let f, what a bad name for a variable, but anyway, of fills. So we want to basically do this thing inside, probably adjust it a little bit, right? So for each of the fields, we want to access its if f.pi pixel index is less than f. I think we name it pixels here, right? Pixels.length. If that's the case, we are pushing. Here is not push fill pixels, is f.pixels, and then we are putting a point at this coordinate. Well, right. I think we need only one more thing, because initially we access that fill pixels. Yeah, here in the set pixel. So this is set pixel will be used by the last fill that is happening. So instead of just we'll probably have to access what is the last structure, and then for that last structure to access its pixels. So it's yeah, so it's probably we can adjust it. So instead of fill pixels, which doesn't exist, let's say fill pixels is actually, it's from the fills structure that we created, is the last element of the fill structure. And I'm going to use here a function. If you're coding this outside codeguppy environment, you have to implement it. Pick is actually looking at the last element in an array, but without removing. It's like pop, but it's not removing it. And dot pixels. Again, if you don't have this function at your disposal, you can create it easily, or you can say fills or of fills.length -1 is the same. but I like that one, .pic. So should be fine at this point. I think, I hope. If not, the program will crash. So let me run it. I'll run it, a small shape. Let me press key. Oops, PI is not defined. All right. It's very rarely when the program runs fine from the beginning. Oops, it's here, f.pi. Small shape, run it. Let's see if we can. All right. So we can have two structures. And if this one will have some, and let's fill the outer one. All right. They are filling just right. And we can see all of them fill. And we have some gaps here like we have in this one, but that gap should go away because it's already filled. If we see a little bit of a pinkish red, it means that fill actually covered that one, just the animation didn't get the chance to, or in animation we are not seeing it. So that's how it got filled. Now, before closing the lesson, let me recap here something really quick and do one last modification to the program. So we started with the fill recursive function, which still should work, right? So let's run it. Let's make sure that it's still working. Fill recursive. If we'll call this one, yep, but the fill recursive has a problem. If we try to invoke it for a bigger shape, it just fails. For small shapes, it works fine, no problem. But if we're trying again for big shapes, it fails because we reached the maximum stack. All right, so that's why we implemented our own function, fill, that it's using the same algorithm as the fill recursive, but by implementing our own stack. And we implemented the stack using an array. In JavaScript, we have arrays can mimic stacks very easily, and we are pushing at the end of the array and we are popping the last element. So basically this is a, how do they call this, last in first out stack. So the last element that goes in is the first element that we pop out. But what about if instead of pop here we use unshift or shift, right? JavaScript shift method for arrays should eliminate the first element in the array, not the last one. Pop is taking out the last one, shift the first one. If we use shift, this whole array structure becomes something that similar to a queue in other languages. So let's see the difference here, because it's a very interesting and subtle difference, but you'll be able to visualize it because we have the animation. So we have a shape, and let's press a key to run it. Notice how the fill is going. It's not going into those directions like left, right, like those scanning lines, but it goes into this kind of a structure that expands. And of course, we'll still fill it up correctly. Let's remember, if we see here the pinkish red, it means that the fill already executed correctly. So this is just the animation. But notice there is big difference. Actually, let's visualize them both at the same time. Perhaps fill here should take a parameter. We can make it take a parameter, which method to use. Yeah, so I'm gonna name the parameter DFS. It's a little bit maybe technical. We didn't go into technicalities here, but the thing is, in the moment we are using a stack, we are actually doing what is called a depth first search inside this structure. When we are using a queue, like with the shift, we are using a breadth first search. It's a little bit technical, perhaps for another lesson. So we're gonna check here if we are passing true for depth. If we are passing DFS true, we are doing a deep first search. We're gonna do pop. Otherwise, we are doing shift. So basically here, okay, we can comment out DFS equal true means depth first search. BFS or DFS equal true means breadth first search. And it's a little bit maybe not fair to use these names because we didn't discuss them enough, but anyway, let's put them differently. DFS selects the fill algorithm, or the fill, yeah, let's call it algorithm. All right, so now we can basically invoke with true or with false. And now let's go here, and when we press a key, we can check if we press perhaps key 1, we should invoke the first method. If we press key 2, it should be the second method. So here we should pass a boolean, let's say key equal 1. Basically on our keyboard. We are passing true. If we press 1, any other key should be false. Right? So let's run it again, and we should see the two methods in action. All right, a pretty weird structure. It should still be fine. Let me draw another one. Pretty weird structure. Should be fine. Press 1 inside this one and 2 inside this one. All right, so now we can see the two ones going their ways. I can still play and define other structures here. Meanwhile, one. Let's have the same one, kind of the same one, and press a 2. And 1, 2, 1. And I think this is what we wanted to accomplish. This is again a flat fill algorithm implemented on Canvas. You can find the program in the chat, in the comments there. Feel free to open it, extend it. If you create your own version, put it in the comments. And with this one, I want to say thank you for watching, happy coding, and see you next time.